Okay, I've got two proofs by induction for you. The first one asks you to prove that 5n cubed plus n is divisible by 6 for any natural number n. The second one asks you to prove that 2 to the n plus 2 plus 3 to the power 2n plus 1 is divisible by 7 for any natural number n. And now the slight difference in strategy here comes from, well, in problem 1, you've got a polynomial in n, while problem 2, you've got a sum of two exponentials in n. So polynomial versus exponential. That'll make the problem slightly different. So let's do problem 2 later. Let's start problem 1, and for that we're going to use a proof by induction. And remember the way proof by induction works, I've got a base case and I've got an induction step. So the base case here is when n equals 1. So let's plug n equals 1 into this formula here and see what happens. So I get 5 times 1 cubed plus 1, and that's 5 times 1 is 5 plus 1 is 6. Okay, and that's clearly divisible by 6, so I'm good. Let's try the induction step. Now for that, we assume that we've shown the theorem that we're trying to prove. We assume that we've shown it for some value k, and we show how that can be used to deduce the result for k plus 1. So assume we've shown that 5k cubed plus k is divisible by 6 for some k. And now we want to show, WTS, we want to show that 5k plus 1 cubed plus k plus 1 is divisible by 6. Divisible by 6, okay? And to get that, what I should do is take this expression and manipulate it until we can see how this assumption we've made, this induction hypothesis, can be applied. Okay, so let's start by manipulating this thing, 5k plus 1 cubed plus k plus 1, and let's expand this cube. So I've got 5, and then some quick math, that's k cubed plus 3k squared plus 3k plus 1 plus k plus 1. Okay, and expanding this 5 out, this thing, distributing the 5, I've got 5k cubed, 5k cubed plus 15k squared plus 5 times 3k plus another k here. So that's 16k. 16k. And then I've got 5 times 1 plus another one here. So that's 6. Okay. Now I need to figure out how to use this induction hypothesis here. That 5k cubed plus k is divisible by 6. How can I use that? Well, somewhere in here, somewhere in this expression, I can take out a 5k cubed plus k. And so there's my 5k cubed, and I can borrow a k from this 16k. I can write this 16k as 15k plus a k that I'm going to borrow. Okay, and all that just to make sure I can get a 5k cubed plus k in my expression. So here's my 5k cubed plus k plus the rest, 15k squared plus 15k plus 6. Okay, in fact, maybe I can rearrange this a tiny bit more. Why don't we move this plus 6 over here and move the rest of the terms over here? And you'll see why I'm doing that, because by the induction hypothesis, this is divisible by 6. Right, 5k cubed plus k, we're assuming by induction that 5k cubed plus k is divisible by 6. And then clearly I've got 6 here, that's obviously divisible by 6 as well. So I've got a sum of two things divisible by 6. So this term here is divisible by 6. So all I've got to do is explain why this last bit, 15k squared plus 15k, is also divisible by 6. Okay, and how can I explain that? Well, note that I can do a little trick here. If I take 15k squared plus 15k, and I factor out a 3, what I'm left with is 5k squared plus 5k. Or, no, better yet, let's write it like this. Let's factor out the whole 15 and a k, and write it as 15k times k plus 1. Now it's as factored as possible. I don't know why I didn't do that first, but what you can see here is k times k plus 1, that's a product of two consecutive integers. And that means that one of k or k plus 1 is going to be even. So I've got an even number here, right? So this bit is even, and this 15 here has a multiple of 3 in it. Well, 15 is just 3 times 5. So I can write this as a multiple of 3 times a multiple of 2, an even number. So this is divisible by 6. Because it's 15 times an even number. So what I've got, what I've got is this is confirmed to be divisible by 6. This 15k squared plus 15k. So that tells me that this whole expression here that I was working with since the beginning, this thing, is equal to this thing that I worked out. Whoops. This thing. And all these terms are divisible by 6. So this thing is divisible by 6. And that's what I wanted to show. Okay, so I showed the induction step. I showed the base case, and I showed the induction step. And that's a proof by induction. I can conclude, therefore, by induction, the claim is proven that 5n cubed plus n is divisible by 6 for all n. For all natural numbers n. Okay, QED. Okay, so you need a little bit of a trick for this one. You need this trick, and it comes up a lot, that a product of two consecutive integers is going to be even. It's a fairly obvious fact, but it's still a little bit of a trick. And when I introduce this 15, that's a multiple of 3. So in total, I have a multiple of 3 times an even number, and that's divisible by 6. Okay, nice trick. Let's try problem 2 and see how it goes with this exponential stuff in it. Okay, so remember I have to prove that 2 to the n plus 2 plus 3 to the 2n plus 1 is divisible by 7. And the approach is the same. The approach is still proof by induction. So let's identify the base case. And again, I'm saying for all natural numbers, so the base case is n equals 1. And in this case, I've got what? 2 to the n plus 2, so n plus 2 would be 3 if n is 1, plus 3 to the 2n plus 1, 2n plus 1 is again 3. So I've got 8 plus 27, which is 35. And 35 is a multiple of 7, so I'm good in this case. All right, and let's try the induction step. Okay, so for this, let's assume that we've already proven that 2 to the k plus 2 plus 3 to the 2k plus 1 is divisible by 7 for some k. And what we want to show is that 2 to the k plus 1 plus 2 plus 3 to the 2, and I replace the k with k plus 1. So 2k plus 1 plus 1 is also divisible by 7. Okay, so that's what I want to prove. Now, there's a little bit of a trick to this one that didn't come up in the last problem, is we actually have to do a little bit more work. Last time what we said, to conclude that that this expression was divisible by 7, I just showed that it was a sum of a bunch of things that were all divisible by, well, it was 6 in this case. And when you take a sum of things divisible by 6, the whole thing is going to be divisible by 6. Now, I can't quite do that in this case, and you'll see why in a second for the second problem. So what I'm going to do is write out what it means for this number to be divisible by 7. And so what that means in this case is that 2k plus 2 plus 3 to the power, or 2 to the power k plus 2 plus 3 to the power of 2k plus 1 is a multiple of 7. That means it's 7 times some number m for some m. Some integer, positive integer m. Okay, and I'm going to need to use this m in the course of my proof. I'm going to have to use this entire equation. So what I want to do is take this expression here, maybe reduce those exponents a bit, so that's 2 to the k plus 3, plus 3 to the power of 2k plus 3. That's how that exponent simplifies there. Okay, and what I want to do is, remember, I want to manipulate this so it involves this expression here. And maybe I can do that because this k plus 2 here, I can match with this k plus 1, and all I need to do is borrow a k plus 2. So let's write that as k plus 2 plus 1. And then I can split up the exponent. So I can say, I can write this as a product of 2 powers of 2. So I've got 2 to the, well, let's just say 2 times 2 to the k plus 2 plus 3 to the 2k. Well, let's borrow a 2 from here. 3 squared times 3 to the power 2k plus 1. Okay, just so that it matches a little bit. I have a 3 to the power 2k plus 1 in both expressions, and I have a 2 to the k plus 2 in both expressions. Now what I'm going to do is use this equation here. Let's bring this power of 3 to the other side. So 2 to the k plus 2 equals 7m minus this power of 3. And let's sub that in for this 2 to the k plus 2 here. So let's write that as 2 times 7m minus 3 to the power 2k plus 1. And then the rest is the same. Let's say 9 times 3 to the 2k plus 1, because 3 squared is 9. Okay, and let's keep going. Let's expand out this 2 to each term. So I've got 14m minus 2 times 3 to the 2k plus 1, and you might see where this is going, plus 9 times 3 to the 2k plus 1, and I've got a common term here. I've got 3 to the 2k plus 1 and 3 to the 2k plus 1 common. So I can factor that out, and what I'm left with is minus 2 and 9. So I've got 7. So what I've got in total is 14m, 14m minus, or plus actually, 7 times 3 to the 2k plus 1. And I can factor a 7 out of that. I've got 7 times 2m plus 3 to the 2k plus 1. And the point is that this whole bit is some integer, positive integer. And 7 is out in front, so I've got a multiple of 7 here. So all I have to say is this is a multiple of 7. As required. And then I can write a concluding statement saying that, therefore, by induction, I've proven the statement. Maybe I'll omit that this time, but you can always write a concluding statement if you want. Anyways, there you go. 2 proofs by induction.